Today I'm going to introduce plate tectonics. Really, we're going to look at the structure of the Earth. We're going to learn how the Earth is put together and how it works before we get into actual environmental issues. Before tomorrow, if you have not signed into AP Central, AP Classroom, you need to create a College Board account. You need to register for my class. You have to join my section, which is APES Grop. I am going to assign some questions through this site tomorrow. If you're not registered, you won't be able to do the homework. 4.5 billion years ago, a bunch of leftover dust from a big cloud in space smashed together to form our planet. Sounds crazy, but that's exactly what happened. All this dust gathered together and slammed together and made new elements through a process called fusion. And the original Earth was hot and melted. Everything was gooey. So the first thing that happened was the formation of layers on our planet. Things that were heavy were pulled toward the middle of the Earth. Turns out that that was iron. And lighter things, we're going to learn about rocks and minerals a little bit. They're made out of mostly what we call silicates, silicon and oxygen. Those floated to the top. The mantle and the crust are made of silicates. Gases also formed layers. You don't see it in this picture, but the atmosphere is layered. What is the reason that our planet is layered? The answer is very simple. It's density. If you look at the density of the planet in the bottom left there, you see that the density significantly increases as we get to the thick iron core. We are the densest of all the planets in our solar system. So if we were to go from the crust to the middle of the Earth, it would stretch all the way across our continent. We've explored almost none of the interior of our planet. So how do we know about all this stuff? How do we know that core is made of iron and it's liquid if we haven't been able to get there? Well, it turns out that earthquakes provide us the information that we need. When we have an earthquake, our equipment is sensitive enough to actually measure most big quakes all the way on the other side of the planet. Those waves vibrate through the layers. And if you know anything about physics, the waves change when they go through solids or more dense solids or liquids. And we see that the waves actually slow down when they hit the outer core. And not only do they slow down, they bend. And so if you look at the diagram on the left, we can use geometry to calculate the exact distances and densities of the materials inside the Earth, because they can only bend based on the rules of physics. The main point of all this is that it's like an X-ray machine, right? If you've ever had an X-ray, they can see inside your body without cutting you open. So we can actually see inside the Earth without splitting it open or without digging it. And that's all created by seismic waves, earthquakes. Could we do this to the moon? See what's inside the moon? We have already. The astronauts put seismographs on the moon when they were there. And after that mission, they actually took an old satellite and crashed it into the moon to create a quake, to create the waves so that the seismographs could measure it. So we have this information from the moon as well. It does not have a rich, thick iron core like we do. One of the reasons we support life and the moon cannot. We didn't call them earthquakes, we called them moonquakes. How hot is it inside the Earth? How could we figure that out? Well, I just said that the middle of the Earth is iron, and it actually is solid, and the outer core is liquid iron. So that means that this boundary right here between the inner core and the outer core has to be melted iron, or the melting point of iron. Do we know the melting point of iron? Well, sure. We can melt iron on Earth. And when we do that, we know that the temperature here inside the Earth, accounted for pressure, um, is going to be around 5,000 to 6,000 degrees hot. And we should answer the question, why is it hot inside the Earth? Well, the majority of the heat is from the original formation. All that leftover energy from all those particles slamming together. That created a lot of friction. And then there also happen to be radioactive elements in the mantle, and those provide energy as well. Now, with all that heat inside of the Earth, the crust is relatively cold, right? Our rocks aren't melted. That distance spreads that heat out quite a bit. But the heat still wants to get out. The heat inside the Earth is trying to get out. And so it moves through any cracks that it can to try to get out to the surface. You can see what we're leading up to here, right? The cracks happen to be where the plates are broken. Now, I mentioned that the core is life-giving, life-providing, and that's because the liquid sloshing around inside creates something called a dynamo. And that basically the Earth is a giant magnet. That's why we have poles. So the North Pole and South Pole. And as that liquid moves around, it creates something called a magnetic field. Now the magnetic field is this giant, it really is like a giant invisible force field around us. So it serves as kind of a shield because there's a whole bunch of particles coming from the sun called the solar wind. They can actually affect our climate. And when the solar wind strikes our planet, it has to get around our magnetic field. If you watch the little video at the top, you see that it goes mostly around our planet. The magnetic field protects us by deflecting the solar wind. But at the poles, some of that radiation sneaks in, and those little blue and purple clouds that you see, you may have heard of these. They're called auroras. There's the aurora borealis, the northern lights, and at the southern poles, it's the aurora australis, the southern lights. Well, that's a phenomenon that is caused by the solar wind striking and sneaking through our magnetic field. When those particles hit the ions in our upper atmosphere, they heat up and glow. Without that magnetic field, our atmosphere would probably be blasted away into space. We've seen this happen on other planets. So it is absolutely a life necessity. All right, as I mentioned, earthquakes are very important when it comes to understanding the structure of the Earth and how it changes. If we plot earthquakes, we get a map that looks like this. And it may be hard for you to see the continents there, but right in the middle is the Pacific Ocean. And so we see this bright green line going around is what we have nicknamed the Ring of Fire. The Ring of Fire is a place where there are just countless, every single year, earthquakes and volcanoes. Now, if we were smart, which we're not, key theme of environmental science, humans are stupid. We live in lots of dumb places where we shouldn't. And you're going to see that over and over in this class. Why did they build a house there? Because they're dumb. 99% of the time, it may be paradise. It may be this beautiful, amazing, exotic island over here, Bali, Indonesia, where all the celebrities go for vacation. But if you're there on the wrong day, where these three plates all come together, we might have the biggest earthquake that we've ever seen. So big that it breaks the scale. And it triggers the biggest tsunami that we've ever seen. And it literally kills 250,000 people in about 10 minutes. This happened, I want to say 2004. Were geologists surprised that a huge earthquake occurred right here? where three plates are crashing together and locking up and releasing stress, of course we weren't surprised. A few years later, 2008, 2010, giant earthquake right here. Huge tsunami, second biggest we'd ever seen, ravages Japan. Rips open a nuclear power plant and creates a terrible disaster. Now, Japan was ready. Japan's been preparing for this. They had all kinds of defenses put in place, and their death toll was much, much lower than what happened down here. But you can see this ring of fire extends across the Pacific and down our west coast. And it's why we have big volcanoes. You may have heard of Mount St. Helens, I hope. Not everybody has now. It's been many decades now. In 1980, we had a huge eruption in Washington. Nobody should have died because we knew it was coming, but humans were dumb that day. And there were, I want to say, 56 deaths because of a volcano in the United States. We don't think of the US as being big with things like volcanoes, but the West Coast is full, Washington and Oregon, even down into California. And then, of course, a lot of people are aware that California is threatened by what we call the big one, this forecasted earthquake that is probably going to happen in the next 20 to 30 years. And it's because of this part of the Ring of Fire. There are deadly and terrible volcanoes all the way down the coast of South America, Chile, and we'll get into some of those details later on. Now, if I connect those lines, we can turn that earthquake map into a plate tectonic map. And it turns out that the Earth is split or cracked or broken into about 15 or so major plates. You do not have to know every single plate name, but this is probably what they're going to ask you about, knowing the different types of boundaries and where they are located. So understanding geography in the map has been a problem in the past. Start with the Pacific plate. It is the largest of the plates, and I'll show that to you later on. You can see, once again, this is the Ring of Fire that touches the continents all the way around. There's something very unique on the western side. See how these are all islands? We actually call this an island arc system. Island arc system. And the reason it's there is because of the way that these plates are touching each other. We're going to look at the boundaries tomorrow, but these are all pretty smooth. See how they're kind of curved and smooth? That means, if you see that on a map, the smooth one means that they're coming together. We call that converging. And when they crash into each other, that's where you're going to get big earthquakes and big volcanoes. So it makes sense that the Ring of Fire is all of these smooth, converging boundaries. Everything's crashing together, and so we get big events. If you look between North America and Europe and Africa and South America, we see that it's not really smooth. It's kind of jagged or zigzag. And you can see that all along the southern hemisphere as well. These jagged boundaries are not smooth and curved. Well, if they're jagged, that means they're the opposite of converging. They are diverging. I think about if you have a couple, two people who thought they were in love and they're pulling apart from each other. The relationship is rough and rocky and jagged. But the couple who is together, it's smooth and they're happy, and we say smooth sailing. So I think of relationships. On a map, if it's smooth, they're coming together. If it's bumpy and jagged, they're pulling apart. If you can remember that, that's huge. That's going to help you out for whatever they ask you on the AP exam. I'm trying to keep it super simple for you. Okay, now that should allow you to look at the map and tell me if I name any two plates, you can tell me if they're moving together or apart. If I look at the Nazca plate and the South American plate, there's the boundary between them. Are they moving together or apart? Well, it's smooth, it's curved, so they are moving together. The Nazca plate is actually sliding underneath the South American plate. So we can plot all this out and make the map more complicated. And here you see, once again, the jagged areas are in red. They are diverging or moving apart. You can see in the key, we call that a spreading zone. And the blue, the ring of fire, that's called subduction, when one gets pushed underneath another one. We'll get to all the other details tomorrow. We'll look at some of these different boundaries and what they really mean. But recognizing diverging and converging from a map is key. Now, California is kind of weird. You see how it kind of, there's just kind of a straight line there? We have a third type of boundary called a sliding boundary. Its technical name is transform. And that's where they're not really moving together or apart. They're moving side by side, laterally. So a whole different situation. It's why we don't really get volcanoes there, but we do still get earthquakes. We will come back to this chart tomorrow because you will need to know several real life examples of these boundaries. Now, what I was showing you in that previous picture was a flat map, which is distorted. Right? Anytime we take a curve and we try to flatten it out, think about an orange peel. If you can get an orange peel off relatively intact and you try to squish it, it's going to tear it, right, if you flatten it out. So when we look at the Pacific plate, you can see just how huge this plate actually is. It takes up almost half the world. One whole side of the globe is that giant plate. Now this map also shows some tiny plates. There's one up here by North America that's really important. It's called Juan de Fuca. And the Juan de Fuca plate, just because it's little, does not mean that it's not powerful. It is sliding underneath North America, and it is the cause of all those volcanoes in Washington and Oregon. Big earthquakes and volcanoes because of that little guy right there clipping underneath. Now, you probably learned about, ever since you were a little kid, you probably learned about the crust, the mantle, the outer core, and the inner core. But we've progressed. And in high school, we kind of stopped using the term crust. It's still there, but we have to understand that not all crust is the same. Continents are very different from the rock that's at the floor of the ocean. The ocean floor is much more dense. It's made of a whole different rock, and it's much thinner. The continent crust is old and less dense and thick. So the Russians, when they tried to dig to the mantle, they actually dug offshore. They were trying to dig right here to get down into that next section. Now you see, we call that the upper mantle, but the top of the mantle is actually pretty hard, just like the crust. And it's not till you get down here that the mantle becomes gooey, or what we say amorphous, flows like a fluid. And so we've renamed it. We call the crust and the upper mantle, we call that the lithosphere. And if anybody ever uses the word plate, like, oh, that's one of the Earth's plates, they really mean lithospheric plate. Lithos is Greek for rocky, and sphere means layer. So the lithosphere is the rocky layer. And the asthenosphere is the gooey mantle that is actually, well, you'll see in just a second, it's moving, it's convecting. Lithosphere, asthenosphere. Better names for crust and mantle. Now, what's actually happening in that asthenosphere is a really important concept that will also apply to atmosphere in a couple of weeks here. It's called convection. So if I ask you, what causes the plates to move? Why do the plates move? The answer is convection in the asthenosphere. Now, that's obviously a computer-generated image on the bottom, but how cool is that, right? We're sitting here right now, bored, staring at a screen, and underneath us, about 30 miles, that's what's going on. You're boiling water on a stove, and you pour in pasta noodles. And if you let them cook, you'll see that they start moving this way. Hot rises, cool sinks, and it's just a cycle. It's a current. Hot goes up, cold goes down, and that's what's happening underneath the lithospheric plates.